after this amazing keynote by Russ Bodick on program synthesis. And Russ made a very great point and gave motivation why complexity and performance in software systems is really far from a solved problem, right? In particular with the decline of Moore's law, where it's much more difficult to obtain performance from modern programming hardware architectures. So in our case, we've been looking at the case of databases here. And if you look at the state-of-the-art in database system implementation, then you will find that most of the commercial or open source database management systems are really these huge, humongous code bases, right? So upwards of 1 million or even 10 million lines of highly optimized C code. And the question is, okay, why are these systems really so big? And one reason is that there's a lot of specialization going on in these systems, right? And that is mostly done for performance reasons. So we actually looked at the PostgreSQL code base, and we found that there are about 20 implementations of a memory page abstraction and about 7 implementations of B-trees. And of course, as we already heard about, well, the demands of hardware architectures are changing. So it's much more difficult to adapt these systems to new constraints, right? So in the case of database systems, one particular constraint is that database performance used to be limited by I/O, right? Reading data from disk, writing data to disk. But that is no longer the case. Nowadays, you can easily buy a machine with a terabyte of memory, and chances are that most of your data will actually reside in memory. So that means that the optimization constraints have fundamentally shifted. Right? I/O is no longer the bottleneck, but compute becomes much more important. And another point is that these commercial and open source database systems, even though they consist of highly optimized C code and have all these specialized data structures and abstractions internally, they are still 10 to 100x slower than custom-crafted, handwritten queries for a particular data analytics task. And one of the key reasons here is that commercial database systems are still generic systems, right? So they interpret a query execution plan that is derived from an incoming SQL statement. And only very recently, the database community has again started to look at query compilation, for example, using tools like LLVM. So what can we do about this situation, right? How can we build database systems going forward that are more manageable and have better performance? And of course, we can sort of take the program synthesis approach and think about, well, maybe in a couple of years we'll be able to derive these big systems just from a set of constraints. But maybe we can take another point of view, right? So we're here at ICFP, and I wear my hat as a fundamentalist functional programmer. I just say, look, instead of writing these millions of lines of C code, I just use my favorite functional language. I use a very, very high-level programming style. I abstract over these things. And then I get a very high performance and very high performance systems with just a very small code base. So do you think that's a good idea? Yes. Of course, we're here at ICFP, right? But if you really think about it, then most people would say no, or, well, I mean, got to be kidding, right? So you want low-level, you're using C for a purpose, right? You want low-level control over the hardware. You really want to be sure that you can manage your pointers and make sure that you store the low-level data in exactly the format you want, right? So most people would say that's a really bad idea. So I would like to convince you that it's actually a great idea, but we need to go to the meta level. Right? So instead of just using a functional programming language to implement the systems, we use a functional programming language to generate the systems. So with a very small code base and very fine-grained control, I can make this humongous system do what I want, play music or run SQL queries. And I will show you some work we did to make that happen. So what I'm going to show you is all done in Scala, but you can do similar things in other functional languages as well. So what we are going to use is a framework which is called lightweight modular staging. And the idea is that, well, we can use the Scala type system to define which expressions are evaluated at generation time and which expressions end up in code that we generate and then execute later. So the basic idea is if I have a regular Scala type like int, string, or in general t, that denotes an expression that is executed now, right? So there's nothing special about it. And we have the special type constructor, which is called rep of t. So whenever I have a rep of int, rep of string, or in general rep of t, then that means, okay, for this expression, generate code to execute later. So this is one instance of a multi-stage programming approach, which was introduced by Taha and shared in the early 2000s. One thing we do in Scala that goes beyond what most other languages do is that we can also override certain built-in language constructs like if then else, so we can just desugar that into a method called if then else, and then we can overload this method call to actually generate a program expression. So we call this language virtualization. So LMS is a framework that has been developed over the last couple of years. There's an extensible IR. There's also support for transformations and certain optimizations like loop fusions and other things. So the general idea is that we want to provide something that is like a batteries included platform here. So how does this work? So let's assume we have this user code here. So it's just 3 statements here. So there's a print line statement, and then there's an expression that computes a string value. So this is a rep of string. So this is meant to be generated code. And then we print out the length of the string. So we have a DSL interface. So this is like a shallow embedding or a tagless final embedding. We have an abstract type constructor rep of t, and then we have methods, in this case infix length, which is the length operation here, and we have print line, which takes a rep of any and returns a rep of unit. Length takes a rep of string, returns a rep of int. So this is just the interface. We have the corresponding DSL implementation. So this is a deep embedding. Right? We say that rep of t is a type of expressions. So in this case, these are atomic. We only have symbols and constants. And then we have a hierarchy of IR nodes that implement the deep embedding. Right? And now then the interface methods are implemented to create the corresponding nodes. Right? So this is a fairly standard combining shallow and deep embedding approach. So when we execute this code, what will happen is we will create IR nodes for each expression. So first we create a print line node, and you notice that this is wrapped in what we call a reflect node to denote that this is a effectful statement. Then we create the operation that computes the rep of string value. We create another IR node that computes the length, and you can see that we have introduced a dependency edge here. And then we have the second print line, and you will notice that now we have a data dependency, but we also have an effect dependency on the previous print line. Okay? So this is the basic idea how things work. And now I'm going to show you what we actually do with databases. So I have a smallish data set here. So this is from the Google Books Ngram viewer. It is not exactly what you call big data, but it's still sizable for my laptop, right? So it's 1.7 gigabytes. And now, if I want to do some data analysis here, one idea is to load this into a database system such as MySQL, right? And we can do this. And I've done this before the talk because it takes a while. So you can see that just loading this data set takes upwards of 5 minutes. And now let's actually run a query on this. So here's just a simple one. I want to look for a keyword in all the rows. And I can fire this off, and we can wait for the result. And we actually can wait a bit more, because this will take about 1 minute to compute. And so you can see that, database systems are not really fast. So on the other hand, I can just go ahead and write a little Scala program to compute the same result. Right? So here it is. I just use a scanner to tokenize the file, go through each line, and have an if-then-else that checks for the keyword. And if that matches, I print out the result. Right? So pretty straightforward. And let's see what's the performance if I run that. Just need to close the window a little smaller. Okay, so this is the Scala version. Okay, so we already get some result, but this is just because it's printing things out on the fly. Yeah, that also takes a bit, but we get a result in 12 seconds. right? And you can see, okay, now the MySQL version has also come back, and this one took 44 seconds. So you can see, okay, by implementing this query in a specialized way, we get much better performance reading. But that's not all we can do. So we can actually go and implement this one particular query in C. And on the C level, we have more low-level control. So we can do things like memory mapped I/O, which will eliminate a whole set of data copying, right? And let's try to run this file, see what's the performance. Nope, there we go. So this is just 3 seconds, right? So you can see from 44 seconds, MySQL specialized C implementation, 3 seconds. So now what I'm going to show you is that we can actually generate more or less exactly this piece of C code from a very, very high-level SQL interpreter. And we can do that in a couple of steps. So here I have essentially, again, the handwritten Scala code. And I can just go ahead and introduce abstractions on the top of this. Right? So this was all handwritten. It's specialized for a particular query. So we really want to do something more generic. So I can start adding a record class. Right? Records have a vector of strings for the actual data, and then a schema, which is the column names. And then I have a method where I can do field lookup by name. Right? So this already allows me to do something more high level here. I don't have to do the individual in.next and then figure things out by index, basically. Right? But the I/O handling and the query processing are still very much intermingled here. So I can introduce another abstraction here, which is a process CSV method, which does all the scanning, and then I can invoke it like this. Just give it a file name and a condition here. So this is much more high level. I can do more generic things with that. But I really want to have SQL statements as input. So let's do that. We're going to define a set of a data type for SQL query operators. Right? So here I have things like scan, project, filter, join, and group by. And then I can also define a little parser that will, from a SQL statement, create this execution plan representation. Right? So this just uses Scala parser combinators, not much magic in there. So now I have this query execution plan representation, and what I can do is implement a little interpreter for that. Right? So I have a function which is called execop. It takes a query operator and then a callback that is invoked for each record. So if I just have a scan operator, then I just invoke process CSV with the file name and the callback. There's also a print operator, which just emits things to the console. And then I can gradually specify the meaning of all the other query operators. And so if I have a projection, then this just means that I'm rearranging the fields in my record, and I'm passing them on to the downstream callback. If I have a filter, then there is a conditional. And I can continue with that with other query operators as well. Right? I can do joins and groupers, etc. So now when I run this, then I'm back essentially to 40 seconds of execution time because I have introduced all this interpretive overhead. Right? But again, we're here at ICFP, so we know about Futamura projections. If I can specialize an interpreter to a given program, in this case a given query, then what I get is essentially a query compiler. And this is something we can do quite easily, in this case, by essentially flipping the types. So what we're doing is in our record abstraction here, where we previously had a vector of string for the field data, we now add this type constructor wrap of string, which means that all the expressions that operate on field values will actually be generated code. But note, however, that the schema just stays a regular vector of string. So what does that mean? That means that only the operations that operate on data fields will end up in the generated code, whereas operations that just invoke the schema will completely be executed at query compilation time. And similarly, the whole record abstraction only exists at code generation time. And now when I run this version, then let me just actually run this. So I have it set up that it's recompiling things in the background. So now I get a new result. And if I just compare the previous handwritten Scala code with the generated code, then you will see that, okay, modulo, variable names, and slight syntactic changes. This is actually the code that we're emitting here, right? So even though we added all these abstraction, like a query interpreter, which is then specialized using very, very high-level code, we still emit the fast, low-level handwritten code here, right? So I'm just showing the Scala version, but the same thing also works for the C version. And just one thing to wrap up the talk. You can, of course, argue that, yeah, I mean, this is just a toy example, and does this really scale? And, of course, what I showed you is really just a toy, but we did some more serious work here. So this is a joint project between the database group at EPFL and group at Oracle Labs. So we implemented a database query engine, which is called LegoBase, which supports the full TPCH database benchmark. And so this is a little more than 500 lines of Scala, so this is about 3,000 lines of Scala, but it supports all of the 22 TPCH queries. And we're getting very good performance compared to commercial systems and also to other query compilers. And this was published at VLDB last year and actually got a Best Paper award there. And yeah, so that's all I have. If you want to know more, we have a website, or come talk to me. And I should also make a pitch that I'm looking to hire grad students, postdocs, and Purdue will also hire assistant professors in programming languages this fall. Thank you.
So I missed one little piece. You said about something about you gave a C program that ran in 3 seconds. Mm-hmm. But in what you showed us, your generated code was still written in Scala, right? So are you actually generating C? It was kind of in the title of your talk was generating C, wasn't it?
Yeah, so we have, I just showed you the Scala version because this is nicer to look at. I can...
but you can generate C as well,
yeah,
right?
yeah, so we're generating
okay.
generating exactly the same C code as here.
Uh-huh.
And I can run it as well, and it also runs it.
Okay, cool, thanks.
Yeah.